In this video, I'm going to show an excellent resource for learning about cybersecurity and also how you can get help for this course, and that is the TCM Security Discord channel. So if you haven't already joined our Discord channel, I will post a link to it down below this video. And there are a lot of really great channels in here, particularly if you want to learn about low-level things. We do have some details about reverse engineering, things like hardware hacking. And in addition to that, we also have the support for this course specifically. So the channel hasn't been created yet. By the time you watch this video, it will though. And the way to get access to that is go into Academy Start Here, which I'm showing, and then there will be a course just like this that says join, and it will be Assembly 101. And then all you need to do is just click on the happy faced emoji here, the upside down one, and then inside of your courses, you will get added to one that says Academy-Private Assembly 101. And then inside of there, you can go to the course chat if you have issues and you want to get some help. Or if you have suggestions, we love to hear about them. You can drop them in the course suggestions channel as well. So that wraps up this video. I'll see you over in the next one. In this video, I'm going to quickly show the different types of content that you'll see in the lessons in this course, and then also where you can find the coding samples for all of the code that we'll be writing in the lessons. So when you take a look at the course curriculum, if you scroll down and take a look at all of the videos, each of the videos actually has an emoji in front of them, which mean different things. So all of these ones here where you see like a teacher in front of a blackboard, that means these are going to be videos where I am just doing either a PowerPoint or whiteboard presentation, and you can just follow along and take notes. There isn't going to be any activities for you to do on your computer. So you'll notice it is a little bit heavy on those in the first section, but I would say about 95% of this course is actually hands on the keyboard writing code. So after we get through that, you'll notice there is a check-in quiz. So for basically each section in this course, there is a 5-question check-in quiz that is multiple choice or true or false. And the scores for these aren't recorded. We don't even see them. They're just here to help you make sure that you understand the core fundamental things that were covered in those lessons. And you'll see each of those check-in quizzes denoted with a pencil emoji. So after we get through these intro sections, you'll notice we have a lot of videos just here with the computer showing. And what these are indicating is that you should be ready to follow along on your computer and actually perform the tasks that I am doing. So you'll see a lot of those as well. The other type of lesson you'll see is this one here with the binary in front of it, and these are coding challenges. So the way that these will work is will give some details about the challenge itself, and then I'll suggest you pause the video and then go ahead and try and write it on your own. And then afterwards, I'll show my solution. And then I put the solution code in a different lesson, just so if you scroll down, it doesn't accidentally spoil it in case you want to look at it yourself. You notice we then have a check-in quiz, and then also for any of the sections where I'm writing code, where you see these paper clips, there is a download to actually download all of the code files in a zip file if you want to have access to them. So every code that we write, every program will be included in those zip files. So that concludes all of the different lesson formats. There's one last thing I want to show you. So if we go down actually maybe to the modern assembly, and maybe let's go into this right syscall. So if you scroll down past the video, you'll notice here, there is all the code that you can copy. So make sure to scroll down past the video. On pretty much every lesson, there'll be something below the video, whether it's a code sample. If I mention there's a link or anything, that's where you can get these. So don't forget that. And then also you can download the entire programs as well at the end of the lesson, if that's easier for you. So that's going to wrap up this video here. I'll see you over in the next one. Welcome everyone. In this video, I'm going to really quickly chat about what we're going to be covering in this section of the course, including the topics that we're going to be discussing, and then also the format of some of the videos and how they will differ from the rest of the course. So in this section of the course, we're going to be covering some very core fundamental topics on how computers and processors actually work at a very low level. So we'll be learning first about some different numbering systems. We'll be talking about decimal, binary, and hexadecimal. And then we will be getting into how processors actually work at a very low level, going right down to how we actually get them to do specific tasks by applying different voltage levels to the inputs at these processors. So personally, myself, I have found these topics to being really core and fundamental to understanding when writing assembly, what's actually happening under the hood. And I think the best way to actually learn some of these topics and to represent them is visually. So to demonstrate this, I'm going to be making use of some whiteboard lessons and some PowerPoint lessons in this section in order to convey the topics. And I know, even for myself included, this is not my favorite way to learn, especially in programming or cybersecurity courses. So what I will promise is that, about 95% of this course is going to actually be hands on the keyboard, following along, writing assembly code. And I will keep these PowerPoint lessons or whiteboard lessons to a very minimal. And we're just going to cover a few of them at the start, just to make sure everyone's on the page and get that core understanding that we're going to need. So what I will say for, maybe a little bit of motivation is that myself, I don't have a computer science background. I'm actually an electrical engineer by training. However, I have been, programming and writing code for almost 20 years now, and a lot of that has been self-taught. And when I started learning at a very low level about how processors work, right down to the level that we're going to start talking about, a lot of things started clicking for me. And I think it's really important to take a little bit of time to dig into that. And that's why we're going to start by covering those topics. So with that being said, I'm going to wrap up this video here, and I'll see you over in the next one where we take a look at different numbering systems. Welcome everyone. In this video, we're going to do a quick discussion about the different numbering systems that we're going to be using throughout this course. So that's going to be decimal, binary, and hexadecimal. And I realize for a lot of people taking this course, this is probably going to be a review. However, if this is something completely new to you, we will cover everything in this lesson that you're going to need to know. And before we hop over to the whiteboard, just a quick note on why we're going to be taking a look at this is because when we get down to these really low levels of the computer, we're going to really be relying on binary and hexadecimal. And you'll see throughout the rest of this course that we're going to be having to have a really good understanding and almost be second nature what binary and hexadecimal represent, and just how we can kind of see the difference or convert on the fly between the two of them and what they actually represent. So with that being said, I'm just going to hop over to the whiteboard right now and we'll take a look at those different numbering systems. So we're going to start with a number system that I'm sure everyone is very familiar with, and that is the decimal numbering system. And throughout the rest of this lesson, we're going to be working with the number 217. Just kind of arbitrarily picked it in order to just demonstrate converting back and forth between these different numbering systems. So decimal itself, it gets the name from deca, which stands for 10. And that's because decimal is what's called a base 10 numbering system. And what that means is that each of these digits that make up this greater number, so 217, well, each of these individual digits, they can be one of 10 different numbers. So in decimal, of course, it's very obvious. It is 0 through 9. And then if we have any digit that, we want to go past 9, well, we just, set it to 0, and then we increment the next one. And that's how we can, keep adding up those numbers. So in our minds, we just see this 217 as 217. We just, automatically know that this 2 stands for 200, this 1 is a 10, and the 7 is actually just a 7. However, there is a formula for how this is calculated. And then, that formula itself, it actually works for any different base of numbering system. So that's why I'm just going to show how we would, calculate this, or how it works for the decimal, even though it's quite obvious. And then hopefully that helps to really hammer home how the other numbering systems work. So before we calculate this, there is one, kind of naming convention that we need to talk about, and that is that the furthest right digit here, in our case, it's the 7. Well, this is called the least significant digit, and that's the same for any different numbering system. The furthest right number is the least significant digit, and the reason it's called that, of course, is that this one contributes the least to the number. So 7, contributes the least to this whole 217. And then the furthest left number, that is going to be the most significant digit. So to make this easier, I'm just going to number out the ordering of these different digits. So of course, the least significant one, it starts with 0. And then we just increment by 1. So this one's going to be 1 here. And then the most significant digit in this case is going to be 2. We got 2, 1, and 0. So the way that we actually add these up is we'll just start from the most significant digit. So in our case, it's 2. And we go the number that's in the slot. So in this case, it's 2. Times the base. So in our case, it's always going to be 10 for the decimal numbering system. And then that 10 is going to be to the exponent of the slot that it's in. So in this one, it's 2. And then we just keep doing this all the way for all of these different numbers. So here, the next one is going to be plus 1 times 10 to the exponent, and it's in the 1 spot. And then we just keep adding them all up. So the next one is going to be plus 7 times 10, and then it's in that 0 spot, the exponent 0. So if we just expand out this math, of course, 10 squared, or 10 times 2, well, that's 100. 100 times 2 is 200. 10 to the exponent 1 is just 10. So anything to the exponent 1 is just the same. So 1 times 10 is going to be 10. And then anything to the exponent 0, just a quick reminder for math, is going to be 1. So this is going to be 7 times 1, which is 7. So if we add all these up, of course, we just proved mathematically that 217 equals 217, which again, like I was saying before, is very obvious, but hopefully this helps you understand how this kind of system works when we go on to the other numbering systems. So the second numbering system we're going to take a look at is binary. And if we just take a look at the binary representation for 217, that is this 1101 1001. And I'm guessing most people already know this, but this is the numbering system that computers rely on. And the reason for that is because it's very easy for computers to just determine between two different states. So generally that's considered on or off, but in reality, a lot of times that's represented as either a high voltage or a low voltage. So this is the way that computers are actually able to store numbers, do calculations, and also get instructions from a program to actually perform different tasks. So binary itself is a base 2 numbering system, of course, because we just have 0 or 1. We just have those two different numbers that it can be. And if we wanted to go then from binary to decimal, we can follow that exact same formula for how we can calculate it. Of course, the very first thing we need to do is start on the right side with the least significant digit. So again, this is going to be 0. And then we'll just go all the way up here. We've got 1, 2, 3, 4, 5, 6, and then 7. And then we just follow this exact same formula here. So we'll start with the most significant digit and we'll go 1. And then we multiply it by the base. So in this time we are base 2. And that's going to be to the exponent 7. Then we just keep going and adding. So the next one is going to be plus 1 times 2 to the exponent 6. I'm just going to skip this one, of course, because 0 times anything is just going to be 0. So we'll skip the 5th position there. We'll go 1 times 2 to the exponent 4. Again, plus 1 times 2 to the exponent 3. We'll skip over these two because they're just going to be 0. And our final one is going to be this 1 times 2 to the exponent 0. So if we just expand this out again, 1 times 2 to the 7 is 128. Plus this one is going to be 64. Plus 16. Plus 8. Plus 1. Just a quick reminder that 2 to the exponent 0 is 1. And that's going to be, if you add all these up, 217. And so that's how we're actually then able to convert from binary over to decimal. So just looking at this really quickly, of course, going from this decimal 217 to binary, we have 3 digits here, and we took 5 more to represent it. We have 8 here. It's just kind of hard as humans for us to actually look at this and read it. And of course, it takes up a lot more space. So that's why we came up with the hexadecimal system, or why the hexadecimal system is used. And that's the next numbering system we're going to take a look at. So the hexadecimal representation of 217 is just D9. So you see now we actually just need those 2 digits to be able to represent it. And hexadecimal is a base 16 numbering system. And the 16 different numbers that we have, so we've got the same as decimal. We've got 0 all the way up to 9. But then we've got A, which is 10, B, which is 11, C, which is 12, D for 13, E for 14, and then F all the way up for 15. And we can then actually just go and use the exact same formula or the exact same method to then convert this from hexadecimal over to decimal. So this one's pretty easy, but of course we just number out the different positions here, starting from the least significant. So this is going to be 0. Then this one is 1. And then we just use that exact same math. So just a quick reminder here, D is going to be 13. So we'll go 13 times our base of 16 to the exponent 1 plus 9 times 16 to the exponent 0. And then if you just do the math for that, so 13 times 16, well, that's 208 plus 9 equals 217. So again, that's just how we can follow that same methodology to convert back from the hexadecimal to the decimal format. And you can already see how that, that was a lot easier for us to do than going from binary, and it takes up way less space. So what I'm going to do is I'm just going to clear this all away here, and I just want to chat a little bit about some of the characteristics of binary and hexadecimal, and why we use hexadecimal in place of binary. Okay, so we've got back this binary representation of 217, and I just want to talk about a couple characteristics of binary numbers and how we describe them. So the first one is that each of these digits, they are called a bit. So in our example here, we've got 8 bits, and 8 bits makes up what's called a byte. So this would be 1 byte here. And then I've kind of got this split here just because it makes it a little bit easier to look at, but sometimes here, half of a byte be referred to as a nibble. And the reason why we would sometimes need to talk about half of a byte and why I have them split here is because half of a byte, or 4 bits, can actually be represented with 1 hex character. And that makes sense because you can think of hex being base 16, and 2 to the 4 is 16. And, the reason why I split this up, and I'll frequently look at it in these nibbles or 4 bits, is because it makes it very easy in my mind to be able to then convert to the hex equivalent. So what we can do here is then, to me, I just automatically know this is the 8 spot, this is the 4 spot, this is the 2 spot, and this is the 1 spot. So this is just automatically going to equal to 9. And then over here, this is going to just automatically equal to that 13, because of course we've got the 8 spot, the 4 spot, that's 12 plus the 1. So we know that that is D. And then we don't have to really think about any shifting outside of these 4 bits in order for us to convert. If we were going to be trying to convert this to the decimal, then of course we're going to have to start, shifting what these 4 bits add up to being outside of just represented by 1 character. Of course, we would need for this one 3 characters or 3 numbers in that 217. So that's why you'll frequently see hexadecimal as a replacement for binary, because it's just so much easier to convert between the two, and it also saves us a lot of space in writing. So throughout the rest of this course, you're going to be seeing hexadecimal used instead of binary, but just think of it as this really easy conversion from binary to hex. So that's going to wrap up this video. I'll see you over in the next one where we take a look at how processors work. Welcome, everyone. In the next couple of videos, we're going to be taking a look at how processors work right down at a very low level and how we can actually issue commands to them to actually get them to do things, and how our computers at the very basic low level actually do things. And the reason we're going to be taking a look at this in this course is because I think it's going to help us a lot down the road when we're actually writing assembly code to understand what those specific commands or parts of the code are actually making the processor or computer do. So with that being said, I'm going to hop over to a couple of quick whiteboard lessons here where we will take a look at that. So let's hop over to the whiteboard now. Before we dig into the lesson, I do just want to quickly mention that, of course, how processors work and their design and the intricacies of them is a fairly complex topic. And what I'm going to be trying to do my best in these next couple of lessons is to simplify that down and show a simplified version of how processors work. And in doing so, make sure that we cover all of the topics and concepts that will be required for us to understand what's happening with our assembly code when it's actually being run. So with that being said, we're going to be taking a look at a simplified theoretical version of an 8-bit processor in these next couple of lessons. And I've got the schematic representation, or a graphical representation of how we would draw that processor up here on the screen. Of course, on the left and right sides here, these are just the pins that we would use for either inputting signals or outputting signals from the processor. And then this is just the body of it here. And it's made out of silicon. And we're going to chat about what's on the inside in the next coming slides. So just to give you an idea of what we're actually looking at, on the left here, I've got an actual picture of a very old 8-bit processor, and you can see how it mimics that pictographic representation. We've got the pins on the side and then our silicon body here. And then on the right, if you're not familiar with this, I've just got the underside showing here of a fairly modern CPU or processor. And I just wanted to show that because even though you can see it's a lot more complex with all of the inputs and outputs, it's still kind of following that same pattern of we've got all these pins that would get seated into the motherboard, and then they would provide both input and output to the different peripherals, and also input from those peripherals into the processor. Okay, so how do we actually get the processor to do something? Well, that boils down to what the actual body of it is made out of. And we mentioned that it was made out of silicon, but more specifically, the inside of processors is made up of thousands to billions of transistors. And transistors are an electronic device that are used for switching. And one of the important things in computer design is that we can actually then make those transistors into what are called logic gates. So inside of the CPU body, which we're showing here, are thousands to, again, billions of these logic gates. And what we can do with these logic gates is we can create circuits out of them and arrange them in fashions that when we apply inputs to these pins, we can actually then make those circuits do specific things. Like if we go down to a very low level, we could make a circuit that just is able to add together two numbers or subtract two numbers, or maybe do division or multiplication. Again, this is a very simplified version. And of course, in modern processors, we would have billions of these logic gates. And even in our old 8-bit processor, we would still be looking at thousands upon thousands of them. And they would make fairly complex circuits that, when chained together, are able to do different operations for us. So I've just shown pictographically here that, we've got 6 of them, but this is really just a pictographic representation to give you an idea that we can, apply inputs through the pins and then have them go to circuits on the inside of the processor. So let's talk about what these actual gates are, and we're going to just chat about 2 of them in this lesson specifically. So the first one is the AND gate, and I've got a picture of it here. You can see that we've got 2 inputs, so A and B, and then this is actually going to perform some logic and then output Q to us. And if you're not familiar with these gates, then the easiest way to actually look at the outputs is through what we call a truth table. And the truth table just shows basically for all the possible inputs that we can have, what output would we be able to get? And of course, these are going to be binary inputs to them. So you can see that with and, we can think of and like multiplication. And so if we have 0 and 0, it's similar to like 0 times 0, of course we would get 0. If we have 0 and 1, well, that's still going to give us a 0. And 1 and 0 is going to give us a 0. And then the only one that is actually true is 1 and 1 gives us a 1. The other type of gate that we'll just quickly take a look at is the OR gate, which is this one right here. And the OR gate has a different truth table here where we can see it's basically like one or the other. So I kind of think of it as addition. So 0 plus 0 or 0 is 0. 0 or 1 is, of course, 1. Same with 1 or 0. And then 1 or 1 is also 1 as well. And there are a few other different types of gates that you'll see. We have exclusive OR, we have NOT gates, and then, of course, we have the NOT AND or NOT OR, which you'll here referred to as NAND and NOR. And they just have similar truth tables, and we're not going to specifically look at all of them because if you're curious, you can just look up the truth tables for those. So again, these gates inside of the processor are what actually allow us to send it commands and have the processor do something for us. Okay, so how do we actually send it commands then? Well, what we're going to actually do is we're just going to be applying electrical signals to these pins. And these electrical signals are going to either be a high voltage or a low voltage, which is generally something like 0 volts for the low voltage and then 5 volts for the high voltage. And this essentially just represents on or off or our binary. So we can actually just think of these voltage inputs here as a binary number, which we're used to seeing here. So instead of 5 volts, we just have 1, 0, 1, 1, 0, 0, 1, 1. And of course, we just flip that over, makes it a little bit easier to read. And then, of course, we can also represent this as a hexadecimal number. So now we can see already where if we are able to apply a set binary input, which is essentially just going to be an electrical signal, then we can have these gates, logic gates, be arranged in such a way that when we apply these specific binary inputs to them, they're going to do something for us inside of the processor. And that's the basis of how we can actually start writing programs and have our processor be able to do something. So with that being said, I'm going to wrap up this video here and we'll pick up in the next one and see how we can actually craft a program and how that would actually make the processor do something. Welcome everyone. In this video, we're going to pick up where we left off in the last one, talking about how processors work at a very low level. So with that being said, let's hop over to the whiteboard now. So just a really quick reminder of where we left off looking at our theoretical simplified 8-bit processor. On the left side of the processor, we have these input pins here where we can input a voltage signal, either 5 volts or 0 volts, and that indicates either a high or a low, or a 0 and 1. And we can actually then just think of that as a binary number. And of course, when we feed this binary number or the voltage signal into the processor, it's actually fed into these logic gates. And we can arrange these logic gates in such a way that we actually have them perform some sort of function, whether that be addition or moving around pieces of memory or something like that. So we mentioned previously, of course, that even on our simple 8-bit processor, there could be thousands and thousands of these gates. And then on more modern processors, we're getting up into the billions and billions of these. So it's really not practical to actually, draw out these different logic gate circuits. And this one I've drawn here, they don't really do anything. I just really wanted to show that, at the basic level, we're taking an input into these pins, and then they flow through these circuits to do something. When we're actually learning about these processors, though, it's a lot easier to just break these down into the larger portions or units of the processor. And that's what we're going to take a look at right now. So the first unit or section that we're going to take a look at is the control unit. And again, So this is just made up of more logic gates, but instead of actually looking at those individual logic gates, we're just going to call it the control unit and talk about what it does. And it does exactly what you would think it does from the name control unit. It essentially is the controller of what goes on in the processor. So it's generally going to take the majority of the inputs into the actual processor, and then it's either going to be, if it needs to move memory around, perform those functions, or send it to different units. When you think about at the very basic level what computing is doing, a lot of it is just moving a number from one memory location to another memory location, and the control unit is going to be able to handle a lot of that. Of course, we're also going to need to be able to perform arithmetic. So we talked about doing things like addition, subtraction, division, or multiplication. And most processors are going to have a special unit that is going to do just that, and it's called the arithmetic logic unit, so the ALU. And the ALU is then going to be filled with all of those circuits that are going to be able to perform the arithmetic we need to do. So for example, it would have an adding circuit. Of course, we're going to need somewhere to store the outputs of those arithmetic functions, and also the control unit's going to need somewhere to temporarily store data. And in order to do that, we have the third section of the processor that we're going to learn about, and that is the internal registers. So these internal registers allow us to store some data, and this is internal to the processor. So you can maybe think about like your computer, how you have a hard drive or RAM, or maybe you're familiar even with the concept of a ROM. Well, that's not this. These are just internal, very small amounts of memory that allows the processor to function. So let's take a little bit more of a deeper look at these internal registers. In our theoretical simplified 8-bit CPU, we are just going to have 5 registers. However, even on a simple 8-bit CPU, we're going to have a lot more registers than this. And when we actually start writing assembly code, we're going to become very familiar with the different registers and what they do. But for this simplified lesson here, we'll just look at 5. And those 5 that we're going to look at is the general purpose registers, so A, B, C, and D, and then the IP register or instruction pointer, which we'll talk about what that does in a couple slides. One more thing about these registers is that each one of them, so for example, A, B, C, D, and IP, well, it's only going to be able to store 1 byte or 8 bits. And that's what's called to or referred to as the width of the register. And that's what actually makes this an 8-bit processor, is that our registers are 8 bits long. So that's the maximum amount of data that we can take in and process in each of the registers. All right, so now that we have an idea of the different parts of the processor, how can we actually send these inputs into it? So we have an idea that, we could set a bunch of 1s and 0s or 5 volts or 0 volts on these inputs, but how do we know which ones? So every processor is going to have what's called an instruction set. And this instruction set then actually lets us know what the processor can do, what instructions it can actually run, and how to get it to run those. So you can see on the right here, we've got this instruction code, which is just an 8-bit binary number. And again, this is when we apply this instruction or this set of binary numbers to the input, then it's going to perform the related instruction. So you can see on the left here, we've got the description. And the first one we've got here is this move A. So if we wanted to move data into the A register, well, this is how we would do it. We've got this instruction code here. And you may be wondering then, well, how do we get actual data passed into the A register? Like, for example, what if we wanted to, put a 2 in here, the number 2? Well, for our theoretical 8-bit processor and for how a lot of them work, the way that it'll work is that our instruction code will set our processor up into a way that the next piece of data that it receives will actually then be the data that goes into the register. Of course, we've also got the move B command here, and this is just going to move data into the B register. And you can see here, it's just 1 bit different from the move A. And generally, if you're looking at instruction sets, you'll see this is very common that it'll be done this way. And a lot of times you won't even see that there'll be like a move A, move B. There'll just be a move, and then maybe there'll be like X's here for these bits, and there'll be some sort of indication that, if you want to do A, well, you set this bit. If you want to do B, you set this bit. Of course, we would also have a move C and move D, but we're not even really going to look at those in this lesson. The next instruction we've got is this addition. So in order to perform an addition, we would send this instruction code, and then it's going to add what's in the A and B registers into the A register.
So you can already see where this move command is coming into play, because in order to do this add, we need to set the registers up to have the numbers that we want to add already in A and B. The last instruction we've got here is this no op or nop, which it just tells the processor that on this cycle, don't do anything. Keep all of your registers and everything the same and just wait and don't do anything. So now that we've got a basic understanding of our instruction set, let's take a look at how we could actually write a really basic program that just takes two 8-bit numbers and adds them together. Of course, we know we're going to need to pass in some of these instruction codes in order to be able to accomplish that. But how are we actually going to do that? One very basic way, of course, we could do is we could get a 5-volt voltage supply, hook some switches up to it, and then, we switch them on for if we want a 1, and then we open the switcher off for if we want a 0. But of course, that's not a very practical way to do that. Realistically, what we need is some sort of way that we can store these instruction codes for a processor to fetch. So in order to do that, I'm going to introduce another chip, which is called a ROM, or a read-only memory. Now, the way that this ROM works is that it's actually going to be able to store data at specific address locations that we can then fetch with the processor. So if we think about the internals of our ROM, we've got all of these different address locations, and they're of course going to all be 8 bits wide, or be able to store 8 bits in them to match up with our 8-bit processor. And each one of these address locations, so we've got address 0, 1, and then all the way down to however big our ROM is going to store then for us what could be one instruction code or pieces of data. So the next thing we need, if we just clear this internals away, is some way for our processor to be able to fetch those addresses. So in order to look at how our processor can actually fetch the data from the specific address locations in the ROM, let's start wiring up the pins of the processor to those on the ROM. So the first ones that we're going to take a look at are these left pins that we've actually already been talking about. And you'll see I've labeled them here as AD, which stands for address and data. And that's because on our theoretical 8-bit processor, and also on most modern processors, these lines are actually bidirectional in that they can write out, and generally when they're writing out the address of the data they want to get. And then when they're reading in the data that is then stored onto the ROM or wherever they're writing out to. So of course, on our ROM, we're going to need to have address lines. And these address lines essentially are what tell the ROM which section of data we actually want to be grabbing. So we'll connect the address lines to the address and data lines of the processor. Now, the ROM itself, the inputs and outputs, they're not actually bidirectional. So we're going to use the pins on the other side as the data pins. And these data pins are actually also tied back over to, of course, the address and data lines on the processor. So you may be wondering, how does this then just not write over to itself? How can we tie these same lines to both the address of the ROM, not actually, just read its data out onto its address? And in order to take a look at that, we're going to need to introduce two more signals. And the first one is going to be the clock. So I haven't really talked about the clock much, but if you've ever heard of processors and the speed they run at, whether that be at megahertz or gigahertz, then you're already kind of familiar with the clock. So what the clock does is it actually then steps us through each set of what the processor is going to be doing. So you can think of the clock input actually as just being this square wave input here, where, on the rising and falling edges of the clock, we're actually going to then be performing some sort of change to what we're cycling through, and that's what actually lets us run through our program. The one key thing to remember, when we're running through this program and actually, talking about the clock, is that generally it's going to be some sort of clock cycle that represents each separate step through our program. So with that being said, we're going to actually need another signal that tells the ROM what direction the data is coming from on the processor, whether it's actually going out or coming in. So we'll just call that this RW, or read-write signal. And this is what helps the ROM to then understand if what it's reading is actually the address lines coming out, or if it should just ignore that it's actually just reading its own data being sent out. So we have this read or write, and when the processor wants to send out to get an address, it will say, okay, I'm writing. And then when it wants to read that data back in, it will say that it's reading. So now I think we have a pretty good understanding here of how this is all hooked up. We can actually start writing out our actual really basic program. However, this video is getting a little bit long, so I'm going to stop this video here, and I'll see you over in the next one where we take a look at actually writing out this program and the specific instructions we'll need for it, and then seeing how we can actually step through that program and how the processor and ROM behave while we do it. So that wraps up this video. I'll see you over in the next one. Welcome, everyone. In this video, we're going to wrap up our discussion on how processors work by taking a look at the instruction set for our theoretical 8-bit processor we've been taking a look at, and seeing how we can write out that very basic addition program using the instruction or operation codes from that instruction set. And then after that, we will take a look at stepping through that program and how the registers and address and data lines on the processor and ROM would actually behave when we execute the different instructions in that program. So without ado, let's hop over to the whiteboard. On the left of the screen here, I've got the really short instruction set for our theoretical processor. And just a quick reminder, so we've got the description here on the left, and this just describes what that instruction actually does. And on the right here, we've got the instruction codes. You'll sometimes hear them called the opcodes. And these are the actual binary representation or binary inputs that we would need to input into the processor to have it perform this instruction. So on the right here, I've got just a mock-up of what our memory is going to look like in order for us to write out this really basic program to add 2 plus 2 together and then get the result. So on the left here, I've got the addresses, and then what we're going to do is we're just going to fill in the contents of the instruction codes and data that we'll need to write that program. The first thing that I want to call out here is you'll see that the addresses actually start at this 11110000 or F0 in hex. So we're actually starting right in what's called the middle of the address space. And the reason that I've done this for our theoretical processor is that in most real-world processors, they're going to have what's called an entry point, and that entry point is going to be the address location that they're going to look at when they first start up. And generally, it's not at the start of the memory. It'll be somewhere in the middle. So we're just going to mimic that by starting at right in the middle of ours at this 11110000. Okay, so let's now move on to actually trying to write out this program here to add 2 plus 2. So if we look at our instructions, we do have this handy add instruction here. And if we look at the description for it, it says that it adds the A and B registers into the A register. So in order for us to actually make use of this add function, we're going to actually have to put some data into the A and B registers. So we're going to start with the move A. So that's going to be the very first contents of our memory. And we'll put in the instruction code for moving data into the A register. So the next thing we're going to do is we're going to actually have to specify what data we want to move into the A register. So for us, that's going to be A2. So we will put the number 2, and we're going to put the binary representation of it. So that's going to store 2 into the A register. So the next thing we're going to have to do is move some data into the B register. So we're going to put the instruction code for moving data into the B register next here. And then, of course, we're going to actually have to pass in some data. So we will have the data that we want to pass in next, which is going to be A2 again. And now we can actually perform our addition since we have the data that we want in the A and B registers. So we will put the instruction code for our addition. And then we'll just round it out with a no operation that we're not actually going to do anything. Okay, now that we've got our program written out here, let's jump back over to our diagram of the processor and the ROM hooked up, and we'll take a look at stepping through this program and seeing how the processor and ROM behave. So now that we've created our short program, and we'll say that we've written it to our ROM here, and this is the memory contents of it, let's take a look at how we can actually step through this program and see how the processor, its internal register, and the pins and the ROM actually behave for each step. So when the processor starts up, it's going to have a little bit of initialization, but what that initialization is eventually going to do is it's going to set the instruction to that entry point that we talked about. And what the instruction pointer does, this internal register, is it points to the instruction that needs to be fetched by the processor. So if we just go to the very first address location here in our program, which of course is this 111000 or F0 in hex, well, what's going to happen then is the processor is going to write out. So you can see we're doing a write, and the address it's going to write out is the address that is in the instruction pointer. So it's this 11110000. And of course, since we're doing a write, that's going to end up on the address line of the ROM. And when the ROM sees that it has an address being written to it, so this is 11110000, of course, to match this address line, well, it's going to go and get the contents at that address location, which, so of course, in the first one for us, it's going to be that move A instruction, or if we look at the instruction code, or if we look at the instruction code, of course, it's the 11110011. So when we flip over to the next cycle here, you can see we're still looking at this address, but we are now reading in, and we have out being written out on the data lines the contents of that address location. And of course, those are being written back over to those address and data lines. But since we're in that read state, we're going to read in that instruction. Now, you'll notice the registers, they aren't actually changing. And at this point, I haven't shown it, but there would just be, kind of randomness in these registers. But we haven't actually changed any of the registers because all we're doing is we're just setting up the processor so that the next bit of data that it reads from the memory is actually going to be loaded into the A address. So let's do that next. See, when we flip over here, of course, the instruction pointer goes up by 1. We're now at F1, which of course is that next address location. We're now back to writing out, and we're going to write out that address location that the instruction pointer is pointing to. And of course, it's this 11110001. And of course, that's being written back out onto this address line. And then when we do our next step here, you can see still we're at that same address location, but now we're reading back in, and we are actually reading in the data or the contents. And that is the 2. And binary, of course, is 00000010. And you can actually see that is being flipped into the A register. So for the rest of the steps through this program, I'm not actually going to show how these bits work because I think this is enough to illustrate how that works. But what I am going to show is how the instruction pointer increments, and we'll see what happens to the internal registers. Before we do move on, though, one quick thing to call it is you may have noticed that for grabbing the contents of each of these addresses, it actually took us a couple steps or a couple cycles before we got on to the next address. And that's because, as I was mentioning before, it actually takes a few clock cycles for each set of memory to actually go through and read it and perform that instruction set. And that's going to differ from processor to processor, and sometimes it actually takes more depending on the instructions. So just something to keep in mind when we step through the rest of this program. So of course, we now got our 2. So in 2 in hexadecimal is still just 2. We've got that loaded into the A register. The next thing we're going to do is we're going to move on to our next memory location. And you can see, of course, our instruction pointer goes up, but nothing else happens. And that's because now we're just setting up that processor again so that the next data it reads is going to go into the B register. So of course, when we step to the next one, we get that 2, and that 2 is going to go into the B register. So now we've got our numbers that we wanted in our A and B register, so we can perform our addition. So when we step through to the next one, we can see we add A and B, and we put it into the A register. So 2 plus 2, even in hex, is going to give us 4. And now we've completed our program, and of course, we've just got the next one as a no-op, which does nothing. Okay, so hopefully that gives you a little bit of an idea of how processors actually work and what is going on with the hardware, or at a very low level when we're actually writing out our program and sending instructions down to the hardware. Of course, this is just a very simplified version of it, and we kind of have really simplified this. We don't even have any RAM or peripherals or anything like that, so there is a lot that's being left out. And if you did find this interesting, or you are curious about how you could actually do this in real life with real processors and all of the things that I've left out, I'm going to leave some resources down below here for some really good free YouTube content of how you can build your own little computers out of either an 8-bit or a 16-bit processor. So with that being said, though, I'm going to wrap up this video here, and I'll see you over the next one. Welcome everyone. In this video, we're going to be chatting about the processor that we're going to be using for the first half of this course via an emulator to write and run our assembly code. So there's two main things that we're going to be talking about in this lesson. The first is just a quick discussion on why we're using this older processor through an emulator to write assembly code. And then the second one is going to be to take a look at the datasheet for this processor and then relate what we were seeing in our theoretical processor that we've been talking about in the previous lessons to an actual real life processor and some of its actual properties. I've attached a copy of the datasheet for this processor to this lesson, so you can download it through that and then open it up, or you can also find lots of them online. So let's hop over and take a look at that datasheet now. Okay, so I've got the datasheet opened up here, and the first processor that we're going to be writing assembly code for via an emulator is the Intel 8086. We can see it's a 16-bit microprocessor. And if you're not familiar with this processor, this is actually a quite historic and influential processor as far as modern computing goes. It's kind of one of the very first ones that put Intel on the map as one of the leading processor manufacturers. And if you actually scroll down just a little bit in this datasheet, you can see, you may notice, so this datasheet is from September 1990, but this processor is actually even older. It was released and designed in the mid 70s. So we're looking at almost a 50-year-old processor at this point. And because of that, you may be wondering, well, why are we even spending time learning and writing assembly for this? And there's two reasons for that. So the first is, of course, you may have already seen from any time you've looked at assembly, if you have, that it's a little bit more of a complicated language to actually learn, and working on these older processors with an emulator can be much easier when we're first starting to learn how to actually write and read assembly. And the second reason for that is you may see that this processor is called the 8086. And this processor uses an instruction set that was named the x86 instruction set. So this is the x86 16-bit variant. And this instruction set is actually still very widely used and is probably the most widely used instruction set still for CPUs. So all Intel and AMD are still using this x86 instruction set. Albeit, of course, we've advanced from the 16-bit version up to the 32-bit version, and now we're up to the 64-bit version. So even if you see a CPU is running, for example, it's called x64, that's just a short form for x86-64-bit. So this instruction set is still used. It has changed a lot, and there's been a lot of features and things added to it. But at the very basis of it, and the basic instructions, those are still going to be reused. So there's a lot that we can learn from this that we can reuse. And finally, if you are still worried a little bit about the practicality of spending time learning to write assembly for this older processor, we are actually going to, of course, take what we learn writing assembly for this processor, and we're going to be doing so for actual modern versions of the x86 instruction set that you can just run directly on a modern Windows computer without an emulator. So by the end of this course, we will be actually writing assembly code that you can run on a modern Windows computer. So with that being said, I did want to just quickly go over some of the features of this processor, and I think the easiest way to do that is looking at the data sheet. And again, the reason we're doing this is just solely to connect the dots between some of the theoretical ideas or things that we had in our theoretical processor with a real life one. If you're not comfortable with reading data sheets, or there's going to be a lot of data in here that we don't even need to look at, so don't worry about that. And we're not going to need to be looking at this later on. Just really want to close the connection between some of those theoretical points. So the first thing is, if we just scroll down, you can see we've got this diagram here that on the right here, this just shows the pinouts. So we're kind of expecting this. This looks like ours, but of course is a lot bigger. Then on the left, we've got all those different pieces that make up the inside of the processor. Of course, we've got that algorithmic logic unit. We've got our registers. We've got this control and timing unit. So all of those things that we were expecting to see, we're seeing, and a lot of the same pins over here. The next thing I want to show is if we just scroll down here and you want to read about those pins or what they do, then you can take a look and read through those. I'm not going to because they're going to be pretty similar to what we were talking about, but just to show that these also exist, of course, on a real processor. And then what I'm going to do here is I'm just going to scroll down to, I believe it's page 26, and we'll take a look at the last thing that I wanted to show. Okay, so I'm down here on page 26 of the data sheet, and we actually have in table 2 here the instruction set summary. So this is pretty similar to that very limited instruction set that we were looking at on the theoretical processor. And we can see on the left here, of course, we get a little bit of a description about what the instruction can do. And then on the right, we get this instruction code, which is actually going to show the binary for how we can actually make the processor do these instructions. So the first one we've got here is this move command. And of course, we've got a few different variations of it, and those are going to vary depending on the additional pins set and the arguments that we pass in. But again, we just have this, command here, this move, and then we have this binary representation of how we can actually get the processor to do this instruction. And if you read through this whole instruction set, you're probably going to see some things that pop out to you, maybe this push and pop. If we go down even further to the second page, of course, we've got our add and we've got some other arithmetic functions. And we're going to, throughout this course, get to know this instruction set fairly well and what these different instructions do. And I just want to show you that, really at the basis of everything our computers do, even on this non-theoretical one, boils down to all these different instructions that we can pass in, and we're essentially just passing in binary to the processor to get them to do those instructions. So that wraps up this video. I will see you over in the next section where we're actually going to start to set up our development environment so we can write some code for this processor. So I'll see you over there.